Ну і, значить, моя доповідь буде про теорію груп. І існують різні напрямки в теорії груп: комбінаторна теорія груп, геометрична теорія груп, measurable group theory, descriptive group theory, так звані самоподібні групи, фрактальні групи. І ось, значить, фото деяких моїх учнів і колег. Колеги Володимир Некрашевич і Ярослав Воробець, бувші аспіранти Катя Ющенко і Ростислав Кравченко, вони зараз в університеті в Тексас Остіні. Дмитро Савчук, значить, завідуючий кафедрою математики, професор в університеті в Саус Флорида, в Тампі, Євген Бондаренко, професор Київського університету, лауреат премії президента, доктор наук, вже професор. Роман Коган, родом з Одеси, працював на Google, зараз, мабуть, якийсь стартап розвиває, мабуть, штучним інтелектом займається, так само, як і Євген Мунтян, працював і, можливо, працює на Microsoft. Так що це от таке, значить, вступ. Стоп, це я трошки перескочив. А тепер нагадайте мені, вже мене трошки тренували, я вже забув, як мені перейти на другий, так би мовити, файл.
Escape, press escape.
Я вже натискав escape. Ага. Ось. Ну, тепер, власне, да, ще Ctrl-L. Full screen. Хорошо. Okay. So, unfortunately, my slides are handwritten. There was no much time to prepare, and I'm not so gifted in this. By the way, previous file was prepared by Dmitro Savchuk, whose name was pronounced a few minutes ago. You see, the main goal is to discuss a growth and doubling of groups. And we will come to groups. But on the way to this, let me maybe begin with more elementary topics. And in each of them, we will discuss growth. And the notion of growth is one of the most fundamental. So let me just begin with growth like in an analysis. Assume we have function f of a real argument defined, say, on interval 0, 0 not included, infinity. And here are a few well-known functions like logarithm, power function, x to the power alpha, let it be positive. Then exponential function, because a to the power x, where a is greater 1, all these functions tends to infinity when argument x goes to infinity. Also, I included functions of the form a to the power x to the power beta, where beta is between 0 and 1. And here is a rough picture of graphs of these functions. And everybody, I think, understands that all of them tend to infinity when argument x goes to infinity, but with different speed. Logarithm is the slowest, then power function grows, then this, I will call it intermediate growth. So a again, base is greater than 1, rise to the power function x to the power beta, beta between 0, 1 is grow faster than logarithm, faster than any power function, but slower than a real exponential function. So we have this main example, and in fact, these three functions, power, exponential, and kind of intermediate, will play the major role in my talk. Logarithm will appear just accidentally. Okay, now I have a problem. I don't see if you see like the bottom line.
Yes, we see the whole. We see the whole slide.
Okay, because there is, this panel of Zoom, which don't allow me to see all. So what is
you can move it. You can move it to the right.
I move from bottom to top. Thank you, Pavel, for helping me. Okay, and so so here is chain of comparisons of growth. So like inequality, but curved inequality. The slowest growth logarithm, the fastest growth this function. And there are different ways to make a comparison of growth. And like to talk about asymptotic, for instance, you may write that two functions are asymptotically equivalent. So each time in my talk, argument goes to infinity. If a limit of ratio is 1, or weak condition, there is a constant greater than 1 such that ratio is bounded from above and from 0, as shown here. Such comparison, but for use of growth in group theory and in algebra in general, because people discuss also growth of algebras and many other objects, it's better to make comparison between functions as follows. So f growth is smaller than of g if there is a constant c greater than 1. With this condition, that if you expand the argument of g by c and multiply by c and add c, then you your modified function will be above f of x for all values of x. And we say that two functions are equivalent if each of one, if we have both directions of inequality. And then, okay, in my talk, there will be a bunch of exercises and a number of open problems. And most of them will be very difficult. But you may try to think immediately, trying to solve, or maybe if you request, I could send you a file of my talk and later you can solve them, and mostly exercise.
It will be posted. It will be posted.
Okay. So shows that any exponential functions with a b greater than 1 are equivalent in this sense. So it means that now we deal only with e to the power x. We can, when we speak about exponential growth, basically we keep in mind like this is the main exponential function, e to the power x, Euler number. Or another exercise, so that if you have polynomial of degree d, and then its growth equivalent to growth of function x to the power d. So the main term, arrow. And in this case, we say that function has polynomial growth because d is integer. Previously, we had x to power alpha. Alpha could be rational or whatever, but if alpha is a positive integer, then we say polynomial. Now, geometric growth. From analysis, we quickly jump to geometry, differential geometry, or to Riemannian geometry. So everybody knows what is a square of the disk of radius r, and maybe in a three-dimensional space, and maybe in n-dimensional space. But in any case, the fact is that in Euclidean space of dimension d, the volume of the ball of radius r with the center at origin is equal to constant r to the power d. Constant depends on dimension. It involves, for higher dimension, it involves values of gamma function. But in any case, the growth of this function, volume of the ball of radius r, when r goes to infinity, is equivalent to growth of r to the power d. So it is a polynomial growth. Now, if we go to hyperbolic space of dimension t, for d equal to, we call this Boyer-Lobachevsky plane Pachevsky plane or whatever. In this case, volume of balls grow exponentially. There is also formula for volume of ball, and from this formula, one can easily conclude that growth is exponential. So one may arise a question, and okay, there are different models of the world. Is world three-dimensional or four-dimensional, Minkowski space or whatever? And now I raise a question, are there spaces of intermediate growth between polynomial and exponential? Honestly, no answer yet. The next topic, languages, growth, and automaton. So the word automaton, like not Kalashnikov, but in mathematical sense, will appear like twice, at the beginning and at the end, if I manage to reach the last slides. Let X be alphabet, so consisting of certain letters, that can be Ukrainian, Latin, Greek. Oh, mathematically, we use usually like alphabet 0, 1, K, K equal 1, 0, 1 binary alphabet, the most important in mathematics alphabet, binary alphabet. And X star denotes the set of all words over this alphabet. So word W is just a sequence strings of letters. And number of letters N is the length of the word. And any non-empty subset in X star is called formal language. Any non-empty set of words. Could be finite, but right now we are interested in infinite languages. And there is a famous Chomsky hierarchy of languages, which begins with regular, then context-free, context-sensitive, recursive, and recursive are defined using Turing machines. We will not get into details of this. We don't need this. We'll stop a little bit just on notion of regular language. But for arbitrary language L, we can consider set Ln of words with length n. L small n is cardinality of this set. And this is function of a natural argument n. N goes to infinity. And we are interested in growth. In growth, or maybe in properties combinatorial of these numbers, of this sequence. So now my functions become functions of natural argument. At the beginning, it was f of x, x was real. Now f of n, n is a natural number. You can extend it to all line if you wish, but it's not important. The same comparison of functions. And for instance, you can consider as L all set of words of, then Ln is just cardinality of x of alphabet raised to power n. Or you can consider a language of this sort, a consistent of words of this sort, and then Ln is 2n. Or you can write a to the power n, b to the power n, c to the power n. Ln will be in fact, I think it's incorrect formula because Ln is equal to 0 when n is odd number. So sorry, some mistake. Okay, exercise, write correct formula. Okay, more tricky example. Binary alphabet, and language consists of all words that doesn't contain subword 1, 1. After 1, next symbol must be 0. So 1, 1 is like forbidden word. This is called sometimes Fibonacci language because it's related to its growth function is related to Fibonacci numbers. And okay, compute. This is a less easier exercise, quite durable. And finally, example Now our alphabet consists of 4 letters: A, B, A inverse, B inverse. And these are AB will be like in future generators of free group of rank 2, free group with 2 generators. So A and B are generators, and A inverse, B inverse are inverses of them. But we can consider formal alphabet consisting of these 4 symbols, and then introduce set of forbidden subwords. 4 words of this sort are forbidden. So after symbol, inverse of it cannot follow. And then let us consider the language of words that doesn't contain forbidden subword. So set of freely reduced words. Exercise compute ln. In fact, immediate answer is almost immediate. 4 multiplied by 3 rise to power n minus 1. At the beginning, you can have any of these 4 symbols, and then you have only 3 options to continue, to extend. So, is everything going well so far? I mean, are my slides visible, and do you hear me?
Yes, it's very good.
Yes, it's good.
Okay, thank you. It's difficult to give talks by Zoom because you don't feel audience, don't see eyes of attendance. Okay, so this sequence Ln is growth sequence of growth function of formal language, and it is bounded by exponential function at most d to the power n, where d is cardinality of the alphabet. And the growth of this could be of various types. You can create for any reasonable function, increasing function, basically you can create language of corresponding growth. And again, within logarithmic, power, intermediate, exponential growth, and exercise, you may try to a language of intermediate growth, say when, sorry, Ln here should be Ln, grow as partition function, exponent square root of n. Now, ending this part of my talk.
But I am allowed, doing this exercise, I am allowed to use infinitely many rules, yes? With some infinite list of swear words that are not supposed to be used in public.
You can use whatever you want, but should be not difficult for you, Professor Ettinghoff, to and even for a smart schooler to create such example, and is really durable. So no restrictions, just any subset of words with growth. But if you add extra condition asking language to be context free, or so-called index, or so-called at all, or whatever, then it becomes much harder, but still is durable. Now, I was going to define what a regular language is, but I see that I'm already started to run out of time. And basically, let me give just by example. So regular language is a language recognizable by finite automaton of type acceptor, that we call acceptor. So automaton is a graph with directed edges labeled by symbols of alphabet. And there must be initial state and some set of final states. In this case, in Fibonacci case, we have a graph shown as this picture. Q0 is initial state. The set of final states is the whole set of states in this case. And we consider pairs that begin at the initial state and end at a set of final states. And for each such pairs, we consider label of these pairs, just sequence of 0 and 1s, which appear when we go through the pairs. And the language accepted by this automaton is described in this way. And then for Fibonacci language, we can use this so-called adjacency matrix and use it to compute growth series associated with growth function, and so on and so on. And here is automaton that accepts this language freely reduced words of alphabet, or this alphabet, It's another example. Okay. Any question, by the way? Now we will talk a little bit about growth of graphs. I attended first two presentations, and they were one was completely about graphs, second was related to graphs. So practically everybody has opinion what is graph. You have some set of vertices and some set of edges joining some pairs of vertices, and there is a variety of notions, directed, undirected, labeled, unlabeled, and so on. We will not get into the details. For a vertex V, degree of vertex is number of edges incident to this vertex, or number of neighbors. If you have a loop, you include counter with loops. And language can graph can be finite or infinite. We will deal mostly with infinite graphs, but study infinite graphs. We quite often approximate them by finite words. And here are kind of group theory related example. One-dimensional grid, just graph representing integers. Two-dimensional grid, graph representing group Z to the square. Four regular, three infinite, four regular. So degree valence of each vertex is 4. Graph representing free group on 2 generators. So we'll come to that later. And we consider graphs as well as groups up to certain equivalence relations. In topology, homeomorphism. In graph theory, isomorphism. In group theory, also isomorphism. So, so we can deform graph without breaking the loops and so on. And you know this famous Kinsberg-Bridges problem and graph associated with it, whatever. But on any graph, we can introduce a combinatorial distance, where a distance between two vertices U and V is the length of the shortest path joining two vertices. There could be many paths. Length of path is number of edges, and we are looking for the minimal length. And this is a distance between combinatorial distance. And then we can fix some vertex as distinguished and consider a function of natural number n, which counts the number of vertices in the graph on the combinatorial distance at most n from this origin, V0. Or what is the same, this is a cardinality of the ball of radius n around V0 in the graph. So we can speak about balls in Euclidean space, in hyperbolic space, in graph also, in group, latent group. So we have notion of growth of a graph. Now graph is infinite, connected, and goes to infinity. So we have growth function of a graph, and we may study what kind of growth a graph may have. But it is reasonable to restrict ourselves to the case when there is constant C such that the degree of all vertices is uniformly bounded by this constant C. In this case, the growth of graph is at most exponential, because you can build, first of all, graph must be locally finite, not to have values gamma of n equal infinity, but it can have a super exponential growth in general. Let us restrict on uniformly bounded degree of graphs, then growth is at most exponential. And in fact, the most interesting case, the most interesting case is the case of regular graphs. When degree of all vertices is a constant, D is the regular graph. And for d-dimensional grid, growth is polynomial, it's an easy exercise. But if gamma is a regular tree and D is greater equal than 3, then growth is of this type, so exponential. Exponential. And here on the bottom of slide is a sequence of finite graphs called maybe Pascal triangle. Sometimes loops are added to make them free regular. And you can consider kind of limit of this sequence of finite graph, which I denote gamma infinity, like you embed smaller graph in larger and continue and extend in one direction, and you get eventually infinite free regular graph. And this finite graph and infinite graph are related to the so-called Hanoi Tower game on free pegs. So many, perhaps some of you in age 4, 5, 6 were playing these games. I think I had such game. So you have n disk of different sizes, and you have to, the task is to move to another stick or peg using Z1, keeping the rule that smaller disk, larger disk cannot be placed on the top of smaller. And the questions are, do this in minimal numbers of steps, do it in algorithmic way. And this infinite graph that was on previous slide, in this case, it has growth of this type. So it's power growth, but degree is not integer in this case. And by the way, my collaborator, Zoran Sunic, and we related a group, Hanoi Tower group on free pegs, and it's very interesting group and so on. Here, the name of famous mathematician Donald Knuth is included, and everybody perhaps heard about his book Art of Programming and many other books. And he visited Texas A&M, and we had a very nice 1-hour conversations. And when he gave a public talk at our university, he started his talk with a joke. So Texas A&M University, what A&M mean? And he said A for algorithms and M for mathematics, algorithms and mathematics. It was, of course, a joke because A stay for agriculture and M stay for mechanics. So in fact, our university is a combination of kind of сельскохозподарська академия и Політехнічний інститут, в основному орієнтований на petrol business. Так от his book begins with exercise of this sort. And one can consider the same game for any number of pegs. So previously it was 3, it can be 4, 5, or whatever. And then the previous exercise becomes hard problem, like find a minimal way, algorithm, and infinite graphs, in this case, have growth of this kind shown at this picture. So it's the result of the Zoran Sunic. So growth of infinite graph is important asymptotic invariant. Another important invariant is of finite or infinite is spectrum of discrete Laplace operator. So let gamma at the moment be a finite graph, and you can consider a JCC matrix and the set of eigenvalues of it, and this is spectrum of the JCC matrix of graph, and if you divide by D, normalize the JCC matrix and consider difference identity matrix minus this one, you get what is called discrete Laplacian on the graph. And this study of spectra is related to wonderful topics like expanders or Ramanujan graphs, and this is related to telecommunications systems and so on. But I have no time to talk about this. One more important thing is a group of automorphisms. of the graph. Here should be gamma. So we are approaching groups. So what is group of automorphism? It's the set of bijection of the set of vertices that preserves incidence. Neighbor vertices must, image must be neighbors. And examples of very, very symmetric graph is a very big group of automorphism, for instance, binary, infinite binary rooted tree. At each vertex, you can choose switch or not switch. And such coloring by switches, not switches, gives you automorphism. And there is uncountably many such automorphism. And you can compose them and take inversion. And in such a way, you get a group. Even more symmetric object is the regular infinite tree group of automorphisms. So these are important example, and mathematicians distinguish vertex transitive graphs when a group of automorphism acts transitively on the set of vertices or not. And now, okay, very important notion, amenability. So originally it was introduced by von Neumann and 10 years later by Bogolubov, but for larger class of so-called topological groups with topology, by Ukrainian mathematician Mykola Bogolubov. And we will come to this a little bit later. And the terminology was completely different and definition was completely different. And then this definition of amenable group, von Neumann was calling it measurable group, and many areas of mathematics, operator algebra, Sist algebras, von Neumann algebras, and so on, dynamical systems, and so on and so on. And in particular, people started to talk about amenable graphs. So now again, and this is related to Banach-Tarski paradox. A few words about that will be said later. But now let gamma again be graph, but infinite graph with a uniformly bounded degree of vertices, as we claimed before. And now let us consider the following important characteristic of a graph, denoted C of gamma, sometimes called Chigger constant, which was introduced by Chigger in Riemannian geometry, but we can use similar thing in discrete mathematics. So you consider infimum, minimum, like kind of minimum, infimum of ratios, a cardinality of the boundary of finite subset E, the set of vertices, to the cardinality of the set. So here is like a set, subset of set of vertices in the graph. And let us call a boundary of this set those vertices that have neighbor which is not in the set, that are joined with, have neighbor which is not in set, so this is boundary. And then we take a number of points in the boundary, divide on the number of points in the set, and take, you get something positive, but you take infimum of this, and a graph is called amenable if this constant is 0. So amenable if this ratio can be made arbitrarily close to 0. And in group theory, we call this condition a Fellner condition. So now we have notion of amenable graph. And as example, one-dimensional grid is amenable because if you take sequence set En consisting of vertices from -n to n, the boundary consists only of 2 points. So cardinality of boundary is 2, cardinality of the set is 2n plus 1, ratio goes to 0. And exercise for you proves that 2-dimensional, 3-dimensional grid are amenable. In fact, any d-dimensional grid is amenable. But also proves that the deregular tree, when d is greater, when d is 2, we get back one-dimensional grid. But when d greater equal 3, is not amenable. So this is some combinatorial good exercise. Now, groups. groups, and as I understand, 25 minutes, correct?
Yes, yes.
Yes.
It is not supposed that student high school knows notion of group. And in fact, I was quite advanced schoolers, like winner of Olympiads, but with difficulties, this notion came to me during the first year of studying in university. But in any case, so group is will begin with any non-empty set G. And we distinguish some element denoted as 1 or as E or as 0 in some situations. And we have a binary operation for any pair of elements A and B of our set. We can associate one more Z element, which is a kind of product, written AB. And it is in general important we write AB or BA, because usually operation is not commuted. And there are axioms that, first of all, operation must be associative. And we have these conditions, then we have a semigroup. If we have this identity element, then we have a monoid, additional semigroup with identity called monoid. And finally, if every element has inverse, meaning elements such that products are equal to 1, then this is A tilde is inverse, then we say that we have a group. And groups are among the most important objects in mathematics in general, especially in algebra. And operation can be denoted in various ways, like dot, star, circle, plus. Plus usually when group is abelian or commutative. When for arbiter AB, product AB is the same as BA. And here is a bunch of kind of obvious example commutative groups. Integer with operation of adding, then 0 play a role of identity, or rational numbers, or real numbers, or positive rationals, but with a product as operation. And now for those who are familiar with matrices and determinant, important group is a so-called general linear group consisting of matrices of size n cross n with non-zero determinant and operation product of matrices. Now I will produce two examples of groups like generated by functions. So we have two functions, f and g, 2x, x plus 1. Inverse functions are this one. Identity element is just function f of x is equal f, and we generate a group by them. So we take composition of generators fg and their inverses. And for instance, if we make the following chain apply to x f inverse, then g, then f again. So starting from x, we will get x plus 2. X plus 2 is corresponds to g square, meaning g composed with g, 2 times applied to g. So it means that we have this relation. We say conjugation of g by f is g square. And the group generated by this transformation is group given by two generators and one relation. So all other relations between f and g are consequences of this single relation. And this is a very famous, very important Bousselach-Solitzer group. It's metabelian group, extension of abelian by abelian. And instead, too, you can put here any k greater than 1.
I think you didn't turn the page. We don't see the page with Bousselach-Solitzer group.
You don't see a page with Bousselach-Solitzer group?
No.
That's strange because I see it. So how it could be possible?
We see only the page. Slava, do you see this page? Mitya?
No, it's just
No, I see the first page about groups.
We only see the first page about groups.
Okay.
Maybe you can stop
page?
sharing and start sharing again.
Do you see this page?
No, no.
Okay, so what we should do?
Maybe you should stop sharing and then start again. I think the sharing crashed.
Okay, stop share.
And then do it again.
And share screen.
Okay, now it works.
Now it works. Good. So sorry. Yeah, by the way, yeah, when a person gives a talk, everything may happen during the talk. For instance, right now, sharing crashed, internet could disappear. Once I was giving a talk in Montreal at meeting of London, Canadian Mathematical Society, 200 people in the room, and suddenly in the middle of my lecture, person come with a huge ladder and started to drill sailing. So everything may happen. Okay, so what I said that this F and G, two generators of the group, are subject by this relation, which comes from this sequence of application to X. And this is famous Baum-Slach-Soliter group, meta-abelian group, extension of abelian by meta-abelian, has exponential growth. We'll start speaking about growth very quickly. And now I think I have to accelerate. So another very...
So I heard that actually this group was earlier described by Higman, this particular one.
It's quite possible. As Arnold was claiming, if something bears somebody's name, it means that he was not the first who introduced it.
So,
Okay.
so then Baum-Slach actually tried to make sure that it is called Higman group, but nobody calls it because it's a part of the family now.
Okay. You see, you know proof very well. Good. But now another amazing example. Now we consider function on interval 0, 1, and just two functions, alpha and beta. So it's a piecewise linear. 1 over x, 1 over 2x, then x, then 2x. And b of x repeats alpha on the first half of the interval, and then mimics alpha on the second part. And the group generated by these two functions, operation composition. And now it is two related groups. Relations are quite complicated. So this is notation for commutator, standard notation, and so R1, R2 are these words. And a big open problem is group F amenable or not. I didn't define yet what amenable group is, but it will come in a few minutes. But group is amenable if it's Cayley graph. So, and we will discuss Cayley graph just in a minute. Yeah. So, what are amenable groups? And roots are in Banach Tarski paradox. Here is mistake. C is missed. Sorry. Banach Tarski paradox, which means doubling. If you have any three-dimensional object with non-empty interior, in particular ball, you can double it. You can split infinitely many pieces and moving in the space, rearrange into balls of the same size without any holes inside or whatever. So really fantastic, I think. If time permit, maybe during questions, if somebody asks me, tell something more about paradox, I will try to use this time for questions. 15 minutes are reserved. But now, so what is amenable group? We have a group, let for simplicity, group be finitely generated. So A1, AM are generators. Then we can define what's called Cayley graph. As the set of vertices, we use just elements of the group, and two elements are connected if they differ by generator. So here we have G, and here we have G multiplied it on the left by generator, one of generators, AI or its inverse. And doing this for all G and for all generators, we get some graph, and it's called Cayley graph. Cayley graph. So it is a regular graph. Degree is 2m. double number of generators, roughly speaking, and multiplication on the right. So this is left version of the right. And if you multiply this pair on the right by some element A, GA, and here A, it shows that multiplication on the right acts as automorphism of this graph. So this graph is vertex transitive. It's very symmetric graphs. And again, these square groups are presented by one-dimensional grid, two-dimensional grid, and so on. And free group on two generators, which is a group given by two generators, an empty set of relations, no relation in all. Its Cayley graph is just four regular tree. Here I was going to explain more details what are elements. So elements of free group are freely reduced words that were explained at the beginning of the lecture. And operation is you just concatenate two words, U and V, but on the border forbidden words may appear, and then you apply free reduction. You just cancel this. You apply this cancellation. It means that one now is empty word, and in such way you get a Cayley graph. And exercise checks that this operation is associative. It's not absolutely obvious. And group is amenable if its Cayley graph is amenable. So amenability of graph was introduced. This definition doesn't depend on the choice of system of generators. It's not difficult to prove. And as examples, all commutative groups are amenable. Free group on two generators is non-amenable. If a group contains a subgroup H isomorphic to F2, then G is non-amenable. Yeah, and as I told, the notion was introduced by von Neumann. So as groups with a left invariant mean, whatever, it's kind of functional analysis definition. And Bogoliubov showed that the equivalent definition is that group is amenable if for any action on a compact set there is invariant probability measure. And did this for topological group. He was not aware of Neumann work. And paper published an article in Visnik Kyivsko Universitetu. And Tarski reformulated notion non-amenable like to be paradoxical or allowing a doubling. Group can be split in finitely many pieces. Such that they can be arranged to get group get using just one part of pieces and second part of pieces. So doubling of a group and m plus n number of pieces is at least 4, and it is 4 if and only if G contains free subgroup on two generators. And a very interesting question is what values this m plus n could take. A lot of story around that. Okay, and and for Neumann, and then later Maclon-Day constructed the so-called class of elementary amenable groups, which includes commutative and larger class nilpotent and larger class soluble groups. I have no time to define what elementary amenable group. And then there was question: are there non-amenable elementary amenable group? And I showed yes. And there are many of them. And this was done by construction of groups of intermediate growth between polynomial and exponential. So I come to final part of my talk. I am almost out of my time, but let me try in 5 minutes. So now we have...
probably questions will not take this much time, so you can probably take your time.
Okay, thank you. So again, we have finitely generated group. We can consider Cayley graph, and we can define a growth function of a group as a growth function of the graph. And then one of the greatest mathematicians of the last 70 years or so, John Milnor, in Students' Scholars Available Journal Mathematical Monthly, formulated conjecture and followed by problem. Conjecture that G has a polynomial growth if and only if it is virtually nilpotent, meaning contains nilpotent subgroup of finite index. The notion of nilpotency is a generalization kind of commutativity. So you have a group and the center of a group is set of elements that commute with all elements in the group, and the identity, of course, is such element, but there could be non-identity element, and this is center. And then you can factorize by center, and a new center may appear. And if after finally many steps you kill your group completely, get trivial group, then group is called nilpotent. And eventually it means there is subgroup of finite index which is nilpotent. And his question was, is it correct that the growth of group is either polynomial or exponential? The first question was answered by Romo, Misha, Mikhail, whose name was mentioned at the beginning. Yes. And the second was answered in negative note by me. And I constructed uncountably a family of 4 generated, then of 2 generated, the so-called 2 groups, infinite torsion groups, and this related to Burnside problem. Every element is periodic, a group is infinite but finitely generated. And among this family, G omega parameterized by oracles, infinite ternary sequences, there were uncountably many different types of intermediate growths. And this allowed to show to get a strong effect first observed by Neumann that in 1938, that there are uncountably many up to isomorphism of 2 generated groups. In fact, there are uncountably many up to quasi-isometry of 2 generated groups. Quasi-isometry is much weaker equivalence relation than isomorphism. So this is the main example of a group of intermediate groups. Again, like we have interval 0, 1, and we have 4 functions, a, b, c, d. Their graphs are, for a, b, c are shown here, for d, no place. So if p is written over interval, it means a transformation that permutes 2 halves of the interval. And if identity is written, it means every point is fixed. And we delete dyadic rational points of this sort, countable set of points from interval, but still we have uncountably many points, and we apply this for transformation in different order, and it is easy to see the BCD commute, and all of them are involution. A square, B square, C square, D square are identity transformation. These are graphs, kind of self-similar. So this part of B repeats A, while this part of B repeats the definition of C, and so on. So this was the first example of really, truly self-similar group. And it happened to have intermediate growths. And now we know that the growth of this function is basically exponent n to this number, which is greater than half, but less than 1. So we have intermediate growth. My estimates were not so good. This was done by Bartoldi, Anna Erscher, and Genk relatively easily. And surprisingly, so far, nobody is able to construct a group whose growth is super polynomial, but slower than the growth of this function.
Yeah, so, is there a formula for this number?
This number is logarithm or some rational expression of a root of cubic polynomial. So one of big problems is a group of super polynomial growths that grow slower than this particular group. And another conjecture means that if growth is lower than growth of partition function, then in fact group grow polynomially, and hence is virtually important result of growth. Also, this group can be defined as a group of automorphism of binary rooted tree. You can easily translate action on the interval 0, 1, defined on previous slides, as action by automorphism of this binary, infinite binary rooted tree. And also this group can be defined as a group generated by states of Milli-type automaton shown here, Milli machine, transducer, sequential machine. So automata are used in mathematics a lot, in particular in group theory. So this is just idea what is Milli automaton. And now back to geometric growth. So core of my results about intermediate growth is that there are uncountably many spaces, say Riemannian surfaces with constant sectional curvature -1 and intermediate volume growth between polynomial and exponential. Remember at the beginning when I started about geometric growth, both in Euclidean space or hyperbolic, growth was either polynomial or exponential, and I realized if there are welts of intermediate growth. So this is kind of approach in that direction, but in fact, it would be better to have the so-called simply connected spaces where every closed loop can be continuously shrunk to a single point with the space, so with intermediate within the space. So to construct such spaces of intermediate growth that are simply connected, equivalent to fundamental group is trivial, or even if there are contractible spaces of intermediate growth. So contractible, intuitively contractible space is one that can be continuously shrunk to a point within the space. And in fact, growth of groups appeared in the USSR in work of Yefremovich and Albert Salmonovich Schwarz, who proved in particular the theorem that growth of universal cover M tilde of a compact Riemannian manifold M coincide with the growth of the fundamental group of this manifold. As an example, if you consider torus two-dimensional, for instance, fundamental group is Z square, growth is quadratic, and cover is R two-dimensional space, Euclidean R2, or D-dimensional torus RD, and growth of fundamental group Z to the power D is the same as growth of the Euclidean space polynomial R to the power D. While you take a surface, close-oriented surface of genus 2 or greater than 2, and its universal cover, you get this Boyer-Lobachevsky plane. And in this case, growth is exponential of the space, and growth of fundamental group, it's group given by 4 generators and 1 relation. Relator is a product of commutators. So big open question is, are there finitely presented groups of intermediate growth? Groups given by finite set of generators and finite set of relators, because all my examples are have infinitely many relators. Okay, that's last slide, fortunately. Now I want to show some, scroll some photos. So Banach Tarski, Alfred Tarski. This is Taras Banach, one of leading Ukrainian mathematicians now living in Lviv, who, by the way, recently in 2024 gave a talk Paradox Banacha Tarskого, Пояснення для математиків. You can find it on internet. You can find slides. I recommend you to look and even to read carefully or listen. So this is kind of how we cut ball, getting two balls of the same size. For Neumann, for Lyubov, Kaluzhnin, Soshansky. So my groups are a group acting on the rooted trees, and they are related to the so-called Vries product. And one of the pioneers in group theory who invented this notion of Vries product was Lev Kaluzhnin, professor in Kyiv, Taras Shevchenko University, and Vitaly Sushansky, my friend who passed away, fortunately, 10 years ago. So Vitaly Sushansky and Nekrashevich is his student, Boris Oleynik, the dean of mathematics department, Oksana Bezushak, and these are automata generating some fascinating group called Basilica group, or Hanoi group on free pairs, or iterating monodromy group of Z square plus I, or a group of intermediate growth. And here are some fractals that we associate with these fractal groups, self-similar groups. And this is Milnor, and this is Gromov, and that's all. Thank you for